Hello, and welcome to the Cryosphere Pavilion and this session on Seabed Permafrost Cathrates. My name is Tom Webb, and I'm a postdoctoral researcher at the University of York researching the coastal cryosphere. This session is brought to you by the Cryosphere Pavilion and is also available at hubs at Geneva and Stockholm. Afterwards, there will be a question and answer session, and you can post questions in the chat or at those hubs. And it will be directed to the host, and then you'll be able to pose your question to the speaker. The first speaker today is Paul Overduin, who is a senior researcher at the Alfred Wegener Institute, and he is here on behalf of the EU Horizon 2020 project named Nunataryuk. Thank you.
Good morning. My name is Paul Overduin, and I'm going to be talking about permafrost beneath the ocean and why it's important for the climate and how it's changing. I'm including contributions from a number of my collaborators in the Nunataryuk project, as well as in Canada. They're listed here. Let's get started. What I want to start with is this picture. If you don't get anything else from this talk, I hope you get these two concepts. One is a pot lid and one is a freezer. And I'm going to try to describe what subsea permafrost is and why it acts like a lid on a pot and why it acts like a freezer and why that's important. So we're going to come back to this picture. That's the key message here for people who aren't familiar with subsea permafrost. What I think is important in the context of ICCI and this meeting here in Glasgow is to talk about the risks. And there's two risks, I think, that are associated with subsea permafrost for the global climate that have been talked about in the literature. One is an immediate risk of a catastrophic release of methane. And there are people who've talked about what that will cost us economically and what that might do to the warming of the climate. And then there's also the risk of a sustained, by which I mean like a long-term release of carbon as subsea permafrost thaws. And those are the two that's the context for what we want to talk about. But in order to assess these risks, in order to understand, are they real? Is a catastrophic release going to happen? Do we have a long-term sustained release of methane in our future? We need to know a little bit more about the system. So I'm going to introduce the system asking these questions. What do we know? So how much methane and how much organic carbon are there beneath the ocean in the Arctic? And can they reach the atmosphere? Can they become a forcing factor for further climate warming? And when will they reach the atmosphere? Will they reach the atmosphere quickly all at once? Will they reach the atmosphere over the long term? That's the kind of questions that we want to be able to answer. So we're going to look at the state of our knowledge and look at what are the important things that we need to know. First, though, I think we need to define some basic terms so that we all agree on what we're talking about, agree on what I'm talking about. What's subsea permafrost? What do we mean by organic carbon? And what are these gas hydrates? The title of my talk, I also talk about Clathrates. So what are Clathrates? What are gas hydrates? And why are they important? How do they figure in? So I'm going to go through these three topics very shortly, just so we're all on the same page. This is a relatively recent map of a permafrost distribution in brown colors on land. The dark brown is continuous permafrost, and the light brown is just permafrost here and there in spots. And the green colors are give you an idea of where we think subsea permafrost is. That's based on modeling results. And the darkness of the green color tells you how thick the permafrost is beneath the seabed. I just want to say a couple of things about this. First of all, there's only about a tenth as much permafrost beneath the ocean as there is on land. So there's less subsea permafrost than there is on land. And almost all of it, most of it's in Siberia. You can see that's kind of in this area from Alaska over to the Kara Sea. We have got the green areas. There's some also north of Canada and Alaska. So why is there frozen ground underneath the ocean is the question that we can ask ourselves. And to do that, I'm just going to focus in just on a imagined cross section of the continental shelf in north of Canada. Looks like something like this. On the left-hand side is the coastline, and we have depth down to 1.5 kilometers beneath the sea level. This dark blue is seawater at the top, and you can see there's a nice flat continental shelf, and then you get deep ocean at some point, 100 kilometers from the coastline. A little bit complicated, but there's a blue area towards the top. That's permafrost. It's frozen in this picture down to about 600 meters beneath the seabed. And then what's happened here is that this permafrost actually got created when sea levels were much lower. So this was land during the last ice age. The ground froze under the cold climate. Sea levels came up when the ice caps melted and covered that permafrost. So it's actually permafrost that formed on land and has since been flooded. That's what we would call subsea permafrost, almost all subsea permafrost. That does something to your typical permafrost to flood it with ocean. It starts to warm it up immediately. Salt water starts to infiltrate into the permafrost. So basically, subsea permafrost is doomed. Once it's covered with seawater, it's got a very stable temperature at the top, very close to its melting point. And we have geothermal heat flux coming from below constantly. So slowly but surely, that permafrost is going to thaw out over a long period of time. There's a couple of other things on this picture that I should explain. One is this dashed red line. That's a zone in which gas hydrates are stable. And I have to explain what gas hydrates are first. But notice that it overlaps with the permafrost and it goes beneath the permafrost. That's the critical thing here. Yeah. So what do we mean by, I'm going to go from subsea permafrost. That was your intro to subsea permafrost. Now we're going to talk about organic carbon and gas hydrates. What do we mean by organic carbon? Organic carbon is your compost. It's plants and animal rests. And in the context of permafrost, they're often frozen into the permafrost. And as long as they're frozen into the permafrost, they don't decompose, they don't decay, and they're not creating greenhouse gases. If you thaw that permafrost out, they decay and start to create CO2 or methane. And that's why this becomes a positive feedback to global warming. The third one is gas hydrates. If you take a look at the picture on the left, looks like ice. These are things you'll never hold in your hand, things that you'll never encounter in nature. Gas hydrates are a cage-like structure of water molecules surrounding gas molecules, and they're only stable when it's cold and when there's a lot of pressure. That means you can find them at the bottom of deep ocean, or you can find them in permafrost where it's cold, deeper, and they can form in the ground, or they can form at the seabed, beneath the seabed. If you set this ice on fire, these gas hydrates, they'll burn. And they set free, if they thaw, they set free more than 150 times their volume in methane. Typically, gas hydrates, Clathrates is the general term. Gas hydrates are Clathrates with gas inside, and typically gas hydrates have mostly methane inside, which is a potent greenhouse gas. This is a picture on the right of a sediment core. If you're lucky enough to core sediments in the Arctic, then you might actually see some hydrates, which will rapidly degrade when they come under normal pressure. Where are these things? Organic carbon is basically anywhere where sediment gets deposited and integrated into the permafrost. In some places, higher concentrations, in some places, lower concentrations. And where, as I say, wherever the permafrost thaws out, that organic carbon decays and creates greenhouse gases. Where are the gas hydrates? They can be found within the permafrost or also below the permafrost. This is what I showed with the overlapping red region with the blue region. You can find them on land, deeper in the sediment column. You can find them on the shelf and also in the deep ocean. Here's a complicated picture that I'm going to use to talk about the pot lid and the freezer again. And I'm not going to go through everything on this picture. Again, you have the coastline, the land surface, and part of the shelf here. And there's a gray region beneath the surface. That's our pot lid. That's frozen sediment. That's the permafrost. It's icy, it's frozen, gas can't get through it. That's the lid on whatever's beneath it in terms of gas. You could have gas coming from oil deposits deeper down, migrating upward through the sediment. Once it hits permafrost, it's trapped, as long as the permafrost stays frozen. As well, the organic carbon in the permafrost can slowly degrade, especially if there are pockets where the permafrost is not frozen, but also be trapped within the permafrost. So you can imagine that when you thaw this permafrost, that you start to produce methane or CO2 or both, and that these then could potentially make it to the atmosphere, exacerbating global warming, which would then feed back to increase the rate of permafrost thaw. So you get this devil's circle of increased warming, increasing the cause of the warming. So therefore, we have two processes going on here. We've got a lid, which is the frozen sediment, and we've got basically a freezer. And the question for us is, how does our lid look, and is our freezer functioning? The lid might be broken, it might be porous, it's a complicated system. There may be holes here and there, or it may be completely thawed out in places. And for sure, the freezer's been unplugged. As I said, once it's covered with ocean water, the permafrost is basically doomed over long time scales. What do we know? The bad news of my talk is that the state of our knowledge, this is a quote from one of my colleagues in Stockholm, it's not scientifically credible to make scientific statements on immediate or sustained risks. And I think that's a pretty broad consensus, actually, with researchers that I work with in Canada and the US. We don't know enough about how much organic carbon is in the sediment. We don't know enough about how much gas hydrate is in and below the permafrost. And we don't really know how much emissions would result from thawing. So basically, that I could just have shown this slide as my talk, and we would be done here. But I'm going to keep going. We're going to talk about what we need to know and how we kind of can tease out some of the details here in terms of the risks. This is, for example, just a very recent paper from Jannik Martins in Stockholm University, where he gathered together all of the organic carbon data that he could for sediment samples that had been taken in the past, basically, for the Arctic Ocean. So it's a map of the Arctic Ocean. The red dots show you where did people measure organic carbon content in sediments, surface sediments or in sediment cores. And a picture sort of starts to emerge. The values are between 0 and 3.5% by weight, more or less. And where you have exchange with the southern oceans, with the Pacific or with the Atlantic Ocean, you have relatively high values, or where you have rivers dumping material from land into the ocean, you have higher values. So this gives us a little bit of an idea of how much organic carbon is getting deposited and potentially incorporated into the subsea permafrost, and where. So at our institute, we did some modeling then to look at over long time frames how much carbon would be accumulated over, in this case, 450,000 years, just in the upper sediment column, using these values. And the value is very large, 3,000 petagrams of organic carbon accumulated. That's more than twice as much organic carbon in land permafrost at the moment. So we have relatively large values, and that means this idea needs to be tested. That 3,000 has a plus or minus of about a factor of 2, so something between 1,500 and 5,000, and really depends on how much of that material doesn't get eroded, how much of that material gets decayed over time. This is a model with decomposition incorporated, microbial decomposition. That's where the uncertainty comes from. So we have a map for permafrost, more or less, of where we think organic carbon is. How much gas hydrate is another question. Here the answer is we really don't know. There are estimates that range from relatively low to high. One here, for example, 20 petagrams of carbon from Rupel in 2015. And as well, in addition to the gas hydrates, there may also be methane as free gas in the pore space in the sediment. Even if we don't know how much gas hydrate there is in the sediment, we can move around with boats. We can measure how much gas we think might be coming out. So there are estimates of how much methane is coming out of the seabed each year, but they range from actually negative numbers, about 0 to about 17 teragrams methane per year. How much is that? I think the numbers for total emissions to the atmosphere at the moment are around 550 teragrams. So that's a relatively small number based compared to natural and anthropogenic emissions. And our methane concentration is increasing by about 17 teragrams methane per year in the atmosphere. So even the maximum amount that's coming out of the seabed at the moment corresponds just to the annual rate of increase that we are causing. What I show on the right here is a short movie of one of our boreholes, which just happened to catch fire. And in general, when we drill through the ice into the seabed and hit a pocket of unfrozen material, it's saturated with flammable gas. So we always have to be on the watch out for borehole fires. just as an example of how we can kind of get at what do we know, what don't we know. This is from my colleague Scott Dallymore at the Geological Survey of Canada. It's a map of the shelf in blue north of the Mackenzie River. The orange lines show you how thick the permafrost is. We have a good idea of how thick the permafrost is here because they drilled a whole lot of holes. All those stars, the red and white stars, are boreholes. They go down up to a kilometer into the sediment bed. And they've been interpreted and mapped in terms of where is the permafrost. And the red stars here show where did they hit gas hydrate. And about 80% of the boreholes hit gas hydrates. So they had to watch out that they didn't get blowouts or explosions while they were drilling. This is something that we know from the deep water horizon, for example, that you can hit gas pockets. But it shows that in a location like this, associated with thick permafrost, we for sure have significant deposits of gas hydrates. There's other evidence for methane stemming from permafrost. On the top left, there's a small film. This is also from relatively shallow water on the Beaufort Sea. And you see the bathymetry, the topography of the seabed, so to say. There's scratch marks, these long lines from ice scouring where big pieces of ice have scratched at the bottom. But these little craters everywhere are pock marks where gas is coming up out of the seabed. Same thing can be seen in other permafrost locations like on the East Siberian Shelf, where there have been many observations of methane coming out of the seabed. The question is, where does that methane come from? Does it come from gas hydrates? What is the actual source? Another way of observing methane emissions is to use a sonar. Here's an image on the bottom, just of bubbles coming up out of the seabed that you can see, like with a fish finder. The critical question, so we have permafrost, we have organic carbon in the permafrost, we have gas hydrates that we find where we have data, we have methane coming up out of the seabed. That gives us some constraints, doesn't really tell us how much, and it certainly doesn't tell us how quickly. We need to have observations over time to see this change. How quickly is the permafrost thawing is question number one. How quickly is organic carbon decomposing in this turned off freezer and turning into methane? And how quickly is gas hydrate dissociating and turning into methane? These are the kinds of questions that we want to get to. And in order to get to them, either we need a long data series where we go to the same place frequently and measure them, or we need to do models. We need to get some model values to predict this. So here's a paper that's just in review at the moment at the cryosphere. What I'm going to show you here are some model results for what happens to permafrost and what that means for organic carbon and for methane emissions. On the bottom here, we have time from 1900 until 2300. So we're looking almost 200 years into the future. The black line gives us the historical rate of subsea permafrost thaw based on modeling. And then I've got three different colored lines here, which are the IPCC socioeconomic pathways. So the dark blue one is the green road. If we manage to reduce our emissions, reduce our climate forcing as humanity. The light blue one is kind of middle of the road where we have a moderate reduction. And the rocky road is kind of business as usual if we continue on the same path of high emissions. What happens to the permafrost? On the y-axis, I have something called melting rate ratio, which means how much of the permafrost, how many times more permafrost thaws relative to pre-anthropogenic forcing before we started warming up the Earth. And what you can see is that until about the year 2100, something happens. For the two moderate scenarios, we kind of have up to 4 times as much thaw. But for the business as usual scenario, at 2100, something really seems to flip, and we start to really thaw up to 15 times, 18 times as much permafrost as we did pre-forcing, pre-human activity. The reason for this is what happens to sea ice. By that time, the sea ice cover on the Arctic Ocean gets reduced to much less than it is today. Less than 70% seems to be kind of a threshold. And suddenly we get a warming of the seabed temperature and more active thaw of the permafrost. What does that do for, or where does that happen? These are the same things again. On the left is the green road, let's say, the middle of the road is in the middle, and the rocky road, if we continue emissions as we do, shows where that permafrost is thawing. And basically, wherever we model permafrost, we have thaw. We can then take that information in the sediment and say, okay, we know where it's thawing, where it's warming up. We have an idea of how much organic carbon there is. What does that mean in terms of how much organic carbon is being degraded in the sediment? And this gives us, for the same three scenarios, different colors, an idea that we're getting up to over 400 teragrams of carbon being degraded in the permafrost per year once that switch flips in the future. So what we're seeing here is that decisions that we make now have a consequence in a century, in 2 centuries, and 3 centuries. So if we're talking about intergenerational justice, or what we're leaving for our children and their children, we're talking about consequences for many generations in the future. Permafrost reacts very slowly, but once you get that train moving, it becomes very difficult to turn it around or to stop it. What happens to this organic carbon that gets degraded? We go ahead and model the microbial degradation and the products of that as gas. So here we have methane that gets produced from this amount. So we're talking about the production of up to 200 teragrams of methane per year. Keep in mind that 17 was the maximum amount that we currently see coming out of the seabed. So that's a factor of 10 increase in the potential amount of methane being produced, and the amount that could then be emitted from the seabed is much less, because microbes tend to intersect that and turn it into CO2, or because we have pathways that are blocked for emission. So even in the most pessimistic scenario, we have what we would look at here as an increase by about double the amount. That's the maximum estimation today. All of this with the caveat, all of this with a warning. There are huge uncertainties in this modeling in terms of organic carbon amounts, in terms of methane production, in terms of methane emissions. We don't know how easy it is to decompose the organic carbon. What did we put in the freezer? Is it easily turned into methane, or is it difficult for microbes to turn into methane? How permeable is the sediment, or will it be once it thaws out? That will control how quickly gas moves through the sediment. How effective is methane consumption by microbes in the sediment? Does that methane get intersected and degraded? So those results have to be taken with a grain of salt. The processes that they show are real. The absolute amounts have large uncertainty brackets associated with them. So back to our state of knowledge. This was my bad news at the beginning. I said it's not really possible to make concrete, credible statements about the risks. We can say what kind of risks there are now. We can say where we think they're going to be coming from. We have an idea about the amount of organic carbon and the potential gas emissions that can result from degradation and from the release of gas hydrates. I'm going to make a couple of concluding remarks just to drive home the message. Subsea permafrost acts as a pot lid on what's beneath it and what's inside of it, and it acts as a freezer, keeping that organic carbon that's been deposited and accumulated out of circulation. Once it thaws, that organic carbon is free and can be turned into greenhouse gases. Our state of knowledge, where we're at right now, is that there are large and long-term potential risks, and that we just simply don't have enough observations. And I have one last point that I would like to make about the not enough observations. And that is going back to this map from the Beaufort Shelf. It's one of the places in the Arctic where we have the best knowledge of permafrost, because we've drilled through it in about 80 different places. That data is now public and has been analyzed by scientists. But those boreholes weren't created by scientists, they were created by the oil industry. So the point here is, we know more than we do. Humanity as a species knows a lot more about subsea permafrost than I can talk to you about. In this case, they're old boreholes, and the oil companies decided that they could either sell or release the data so that it could be used. But the question is, who's paying for knowledge? We pay for it when we purchase gasoline at the pumps. The budgets for research and development by oil companies for work looking for new deposits, for new resources, outstrips the global climate research budget by an order of magnitude. Once they have the permission to look for oil, they move in, They did so in 2012 in the Eastern Siberian Sea for a few years until it became politically difficult. They did so also in the Beaufort and Chukchi Seas. And there's a mass of data there, most of it geophysical. And for sure, some of that's relevant to subsea permafrost and to the deposits within subsea permafrost. As a species, we know about these things, but that information, that data belongs to people who can make money with it, selling us fossil fuels. There's a tremendous irony in that situation from my perspective. Thanks very much.
So thank you very much. That was really insightful. I found it very interesting. I have a question, but before I do, I want to ask if anyone on the floor has a question or perhaps anyone on the chat.
Hello. Oh. So you showed quite a horrifying graph of the green road, the middle road, and the rocky road, and you said that the rocky road is largely defined by the behavior of the sea ice beyond 2100, but the behavior of sea ice beyond 2100 is like really uncertain in the models. So, I mean, how much do you trust the permafrost behavior that depends on that beyond that long horizon?
So, I think again, what I'm trying to say is that the processes behind that are quite clear. So it's the 2100 date may have a lot of uncertainty associated with it. That sea ice is disappearing in the Arctic is already clear. The question is more or less when. What the model shows is that when that sea ice disappears below a certain threshold, for sure we get a coupling between the atmospheric temperature and the seabed temperature, and that will for sure mean an acceleration of permafrost thaw.
Thanks.
Does anyone else have a question? Do you?
I was wondering what your thoughts on are too as we look further out into the future and we just think about some of the kind of where warming ocean water has been able to get to, what the timeline for that is, and if that looks substantially different kind of past that 2100.
That is a good question, and one that I'm not really capable of answering. We already see intrusion of southern ocean waters from the Atlantic, for example, up onto the shelf edge, or also through the Pacific, from the Pacific into the Chukchi Sea. And that's for sure increasing, or is projected to increase, and will also then help move up the shelf. If it moves up the shelf far enough to start to affect subsea permafrost temperatures, I'm not sure about, and certainly not about the time.
So I had a quick question, and it's more of a generic question, but I noticed that your talk was very unique in the talks that I've seen at COP, and I was just wondering, really, it's really also aligned to your final thought, but do you think that this work is being taken into account enough at COP and in the community? And what would you do to, what do you think should be done now in terms of funding to promote this further?
That's a bunch of questions that are difficult to answer. I don't think that this is taken into account. And one of the reasons is because of all the uncertainty and the poor state of knowledge. It makes it very difficult to include subsea permafrost, future estimates of emissions into models or projections because the uncertainty brackets are just so large. I think there's a growing awareness for sure. I can't remember the second part of your question, but
it was along the lines of
yes.
If you had a message
Yeah.
to deliver here about the state of the science, what would it be?
I don't want to get too revolutionary, but I do think that we talk about divesting from fossil fuels. That's certainly one approach. I also think that, to some degree, sharing data is something that would help us to get more precise ideas of where we're headed, what trajectory we're headed on. And the question would be if that's something that, commercial interests could be combined with kind of larger climate emergency interests.
Okay, so thank you very much to our speaker, and I'd like to invite everyone to just say thank you very much right now. Please stick around at 11:30 or come back at 11:30. We have a session on committed permafrost emissions and intergenerational justice. Thank you very much.